And welcome back into this week's Learning with Lindsey. If you have anything that you would like to learn about weather-wise, you can email us at weatherquestions@wreg.com. I do this weekly, but this week I'm going to do the topic for how a tornado forms. Last week there were a lot of storms up in Illinois, and I happened to be there, and while I was in Illinois, mostly central Illinois, few tornadoes were forming, but there were a lot of supercells. There were also a lot of ingredients in the atmosphere primed for tornadoes to form, but not as many did as what most meteorologists were expecting. So I just wanted to go over what you need to produce a tornado and how all of those ingredients come together. First main ingredients that you're going to need to produce a tornado to get a rotating supercell is going to be vertical wind shear, unstable air mass, moisture, and a lifting mechanism. What does all that mean, right? Quite a lot of big words. Vertical shear, you're looking at directional and speed, and that's how the winds are rotating or increasing with height. So at the surface, we're going to go over that in a moment, but at the surface, how the winds move from, say, east to west, or how they're increasing with height. Unstable air mass and moisture are kind of one and the same. You need warm, humid air, and that happens a lot before a cold front moves in. We see temperatures and humidity all ramp up right before a cold front approaches. So that's another ingredient that we need. And then finally, that lifting mechanism, which is a trigger to fire these storms off. And of course, it's a cold front or even a dry line. You can get some rotating supercells with the dry line as well. But how do all these pieces come together? What we're looking at first is going to be that vertical wind shear. So this is, again, how winds are rotating and increasing with height. Firstly, that directional shear, what you need is rotating clockwise, and that's going to be called veering winds. So that's what you would need to produce this rotating column of air. And you can think of it as kind of like a football. When you throw a football and it spins, that's what we're looking at when we want directional or veering winds for that directional shear, as you know, it's approaching a cold front moving in. Backing winds is going to negate that whole thing. So if you have any backing in your winds, it really just wipes out the ability for a rotating supercell. And then speed shear, you also want winds increasing with height. So here at the surface, a little bit slower, calmer winds, and then as it moves up into the top of the atmosphere, those winds will continue to increase. Typically, we're looking at the first 10,000 feet above the surface, from where we are at the surface to about 10,000 feet up. That's what we're really looking at when we're going over this directional and speed shear. And you need speed at the surface to 10,000 feet to increase by 40 to 45 miles per hour. Now, moving to the next step, you need CAPE and moisture. So this is what we're talking about with the unstable air, or maybe a lot of energy. We measure that by CAPE, which is convective available potential energy. And then moisture, you need a lot of humidity and you need that air to be pretty warm. Because what happens, we know warm air rises. So what this warm air is going to want to do is going to want to rise. So the ability of how that cooler air is kind of holding it in place at the surface builds instability and it builds buoyancy. And that's what we're waiting for with this CAPE. We're measuring how unstable that surface air is and how quickly it can rise with a trigger. So it's the measure of, basically it's a measure of buoyancy. How quickly, it's like a balloon. Think of it with helium, how quickly it's going to want to rise without something there in kind of blocking it. As it does rise, moisture will condense and release into what we call latent heat, and that's a little complicated, but really you have to think of it as just a hidden energy source. So this is the measure of energy for fueling storms, not necessarily to trigger storms. That's what we need a frontal boundary for. We need a lifting mechanism. Typically, with all the elements in place, you know, we could have, and we have had, all of the ingredients present in the atmosphere, the shear, the unstable air mass. But if we don't have anything to force that air to rise rapidly, then we won't have towering cumulonimbus clouds or supercells or even rotating supercells. So there may still be a cap and we've talked about this before, you may know what it is. You can think of it as a lid. If you put a bunch of Mentos in a Coca-Cola bottle and then screw the cap on, nothing will happen. But if you take the cap off, all of that Mentos Coke combination will just explode out of the bottle. So that's what the cap is on our environment. It limits that buoyancy, so it holds that warm air at the surface, and that continues to just build and build all this unstable air or energy right at the surface. So when the longer you have a cap in place, say it breaks mid to late afternoon, you have a cold front come through to force all of that air to rise even more rapidly, then you're looking at a pretty volatile environment. But if you don't have this lifting mechanism, cold front or dry line, then you might not get anything at all. So all of these ingredients are important. But how do they come together? When you're rising air, well, first you've got, wind shear, directional shear, speed and directional shear. It starts as a rotating column of air horizontal, so like think of it kind of parallel to the Earth's surface. But then with rising air, because of buoyancy, you're going to see that rotating column of air lift more vertical. And of course, that is rotating in a vertical manner, means we're going to see that rotating updraft supercell form. At some point, when this supercell starts to mature, you're going to see the downdraft form. You have two downdrafts that are critical for a supercell or for a tornadic supercell, to be specific. You have your forward flank downdraft, and that brings all of your hail, all of your rain, that rain cooled area to the northeast of a storm. And then you have what we're looking at right now is your rear flank downdraft. It's a little smaller and it's more on the backside of your storm, and that's going to be bringing down your rotating updraft. It's going to be bringing it back down and causing that air to rotate around it, bringing a wall cloud down, a tornado down. So that's critical for the development of a tornadic supercell. Eventually, as it continues to mature, your rear flank downdraft, which is over here, and then your rotating updraft, because they're rotating in opposite directions, they're going to start to rotate around each other. And then right there in between how these are rotating, you're going to see this little funnel boundary kind of in between those two rotating updraft and that downdraft, and that's where you are going to see the tornado form. So that rotation is being brought down by your rear flank downdraft. Eventually, first, you'll see a wall cloud develop. You may not always see that tornado be brought down to the surface, but you'll see a wall cloud initially, and you can see it right there. It's just this lowering of clouds, and then that tornado will form to the surface. So this is what it looks like in real life when you're looking at a storm, when you're looking at a supercell. So you have your updraft, you've got your inflow over here, and then it'll hit the top of the atmosphere, and anvils, that's what we call it, it's an anvil, where it hits the top of the atmosphere and it still has so much energy, it goes past what it should, and it'll start to spread out in all directions. So that's a signal that we're going to have a very strong storm, very strong updraft with that anvil cloud. We'll have that forward flank downdraft, and there you can see that's where the outflow is, that's where the rain is, the cool air, and you'll typically get a bit of a gust front with this because all of that mass is coming down and hitting the surface at a very, very extreme pace. Then that rear flank downdraft, it's in the rear of the storm. Can't really show it on a two-dimensional picture, but it's in the rear of the storm, and it's going to be near that rotating updraft. And that's what brings down your wall cloud, that rotation down to the surface. So, as you can see, a lot of ingredients are in place when we're watching for tornadic activity. And if we have all the ingredients in place, and if we have a frontal boundary that we're expecting to move into the area, then they're likely, National Weather Service or the SPC is likely going to issue watches ahead of this. Sometimes a couple of hours, sometimes if we've been tracking this for several days, we've been watching the models and they're trending all in the same direction, it could be issued maybe even a day before. And we also are looking at that risk. The SPC outlook shows basically that just several more days out. We can get a 1 to 3 day outlook or a 4 to 8 day outlook, which is a little less consistent, that 4 to 8 day outlook, you sometimes only get to see if it is an extreme risk and it's just been consistent for several days in a row. That's when they would issue, hey, here's a 10% chance, here's a 15% chance that this could happen in that 4 to 8 day outlook. But we're really looking at that 1 to 3, and we have different levels, and we even, a new addition this past spring, the SPC has brought out this conditional threat outlook on top of our regular SPC outlooks, where you get your marginal risk, slight risk, extreme risk. We have this conditional risk that adds, if storms do form in this area, you're looking at extremely, extremely damaging storms. If they don't form, then we're good, right? So there's a lot to prepare for when it comes to any type of tornadic activity, but there's so many ingredients, and even if just one of those things is off, you might not get anything. So that was a look at how tornadoes form, how the ingredients come together. And again, if one ingredient is off just by a little bit, you might not get anything at all. So it can be very complicated, but if there are any other complicated topics that you would like to discuss on our Learning with Lindsey or even our Weather Lounge podcast, you can email us again.